So, good afternoon. With Team LunAR-X working to reshape the moon. To introduce the team, we have Vibhakar, Vivek, Hariharan, and Anish. I am Dhruv. So, this project was made possible due to the guidance and support of our wonderful sponsors, both Red and Caterpillar. Humanity has come a long way since the first moon landings. And space is not just about exploration anymore. It is time to start building things. And there are many people around the world that are working full steam ahead to ensure the future of our species in space. We'll need extensive infrastructure out there, but there's a catch. It's extremely dangerous for humans to be out there building stuff, especially in those hefty spacesuits. But it's a perfect opportunity for robots to shine. So, how will this endeavor look like? After a roughly 3-day journey and a few critical moments of landing, by the time our robot reaches the moon, the operators back home will already have a task ready for it. What will that task be? So, to ultimately build complex structures like habitats and landing pads, we need to start with the fundamental shape of construction. That is the berm. These berms, if you build them bigger and bigger, these can help us build those landing pads. What are we going to use to build this berm? Something which is abundant on the moon's surface, that is lunar regolith, the coarse sandy material. We will require a lot of this regolith to realize our endeavor. And that is where our robot comes into the picture. The Lunar Autonomous Regolith Excavator, or LunAR-X for short, built for this exact purpose. What does it need to start building? The first thing it needs to know is what to build. The operators will tell it how tall and long the berm should be. For today's demonstration, we are building a curved berm. The second thing it needs to know is where to build. So again, for today's demonstration, we've already built a part of the berm to save the audience's time, and we'll be completing it. So here's a video of us building this berm just before the demonstration. So the robot has everything that it needs now to start the operation. Today, it will be teleoperated by us. Let's begin. The robot will first move and start excavating the material. So let's talk a bit more about this excavation. What do we use here on Earth to collect and excavate material? We use the big wheel loaders that have been perfected over the years. When these loaders go to collect sand, the more sand they collect, they're met with higher and higher resistance forces. And the loaders can overcome these resistance forces because of the traction that they have. How do they get this traction? Because of their heavy weight. That means weight is a key critical component to excavate huge amounts of material here on Earth. But we don't have as much weight on the moon. The moon only has about 1/6 of the gravity of Earth, which means we have a much lower weight there. So one big scoop to excavate will not work that great on the moon. What should we do instead? We can have multiple small cuts and scoops. And that is where the NASA's Razor platform comes into the picture. Developed by NASA, this has 2 drums which have multiple cutting surfaces that enable it to excavate under lunar conditions. And inspired from this Razor, we built our own moon loader and excavation drum. This excavation drum has 4 cutting edges. It is built using steel and aluminum, and that allows us to excavate under the lunar conditions. We can rotate this drum in one direction to fill the drum. We've kept the sides of it transparent so you can see how much of the sand it is collecting. Once it has reached its capacity, we can rotate it in the opposite direction, in the other direction, to deposit all of the material. When we deposit it, it assumes a berm-like structure, which you can see looks like a pyramid stretched along one of its sides. After we've deposited all of the material, we have part of the berm ready. So how much can our robot actually excavate? This robot is capable of excavating approximately 9 kgs or 19 pounds of sand per excavation cycle. And each of this excavation cycle takes about 3 minutes to complete. If we were not constrained by the battery power, this robot can excavate over 2 metric tons per day. Now, before moving forward, as you see this robot excavating, are there any questions from the audience? So there are parts of autonomy that we've built in, like the localization and the perception stack, but none of it is making its own decisions right now.
So even how far you go down into the ground.
So yeah, right now it's operated by us.
Follow on to that, though, looking forward, what do you think challenges autonomy?
So the biggest challenge is to figure out how much should we lower the drum, because if we lower the excavation tool too much, it will start being hindered by the sand. It will get stuck in the sand. That, I think, is the key component. For otherwise, the perception and stuff, we've already developed it, we're testing it, so it shouldn't be that difficult. Yeah. Right now, the robot is being teleoperated, but moving forward, we plan to incorporate autonomy into the robot. However, before we have full autonomous function, there are a few critical components required for it. Let's go over them one by one. The first thing that the robot needs to know is where it is in the work site, especially because the construction sites can be huge. Here on Earth, we have a very convenient technology, which is the GPS, which can tell us our position. But on the moon, we do not have this infrastructure yet. So what do we use? We first use the total station that is on the corner of this work site. It has a camera which uses a laser to track the orange prism mounted at the highest point of the robot. Secondly, we use the encoders, which are attached to the wheels that tell us the velocity of the robot. Lastly, we have an IMU on board, which can tell us where the robot is facing or heading. So to test the accuracy of our localization system, we conduct something known as the loop closure test. We make the robot go in a loop, come back to its original position, and see if the sensors also tell us that the robot is back at the same position. If it does, that means our robot can track its position accurately. So before this demonstration, we have conducted a loop closure test, and here are the results. This multicolored frame represents the robot. And you can see in the video, we're completing a loop, and even the sensors tell us that the loop is being completed. Our localization system is pretty accurate with an error of just 2 centimeters. And this is because the total station is highly accurate. The second component of autonomy is that the robot should be able to see what it is building, which is why we have a camera mounted just below the orange prism. This camera can be used to map out the surface and also plan its movement in the workspace. How will the robot know that it is progressing, that it is building properly? For that, we have the camera that can determine the length and height of the berm that we are building. This can be evaluated to get our progress if it's completed to build the berm. Another thing that the robot needs to know is when it has collected enough sand. It needs to know if the drum is full and we can start depositing. Simply put, the more sand that is there inside the tool, the more power will be required to rotate the drum and lift it up. that is how we can calculate how much sand there is in the excavation tool. If we have more sand, it would require more electrical power to lift and rotate the drum. The last component of autonomy is planning. The construction sites can be huge. They'll have multiple zones to excavate, collect the material from, and deposit the material. And our robot should be capable of planning out its operations in such a way that it can build extremely efficiently. All of these components put together will allow it to function autonomously. To summarize, we've built a capable excavation machine that has a drum which can excavate under lunar conditions. As promised, our robot has almost finished building the berm right in front of you. And it can track its own position, and it can evaluate what it's building, the berm that it is building. Moving forward, we plan to develop the mapping and operations planning part of the autonomy stack, bringing it all together at the end to have an autonomous construction machine. We want to also extend our special thanks to Red, Eric from Caterpillar, the senior Crater Grader team for all their help, and Tim, Chuck, and Abhishesh from the Field Robotics Center for the constant support in testing and help building this thing. Thank you for attending our demo. And if there are any questions, we'll open the floor for that. So we have the point cloud, which is visible on this TV. I think so it's stopped right now. Just stopped after operation. But using that point cloud, we can estimate the length, height, and width, the whole metrics of the berm. Right now, because it's a continuous berm and we haven't implemented the mapping of the entire work site, we cannot estimate the full volume of it. Yeah.
This localization part of the evaluating localization.
So we to save time right now, during SVD, we demonstrated the localization accurately. Because we wanted to build a bigger berm for the Encore, and that's why we aren't showing the localization, but we have conducted extensive tests just before the demonstration. Yeah.
I know I asked the last time about what the most common, or at least a good application would be for building the berms, and you mentioned a glass barrier.
Yes.
And I assume you don't need too much accuracy in the shape for that. You need a lot of stuff.
Mm-hmm.
But are there other applications which you would need more accuracy in the shape that you build, and is that something that you guys are aiming for, some accuracy of shape form?
Yeah, so we are going to be aiming for the accuracy. We are going to use a Faro scanner, which is a highly precise scanner, to evaluate how accurately our berm was built as compared to what we originally wanted to build. And talking about the application, so maybe the landing pads may not be that accurate, but if you want to start building proper construction sites for habitats and so, then the layouts will have to be pretty accurate. So yes, accuracy is important there. We have error metrics for the berm that we have a tolerance of the error in the height and length of the berm, and that is how we define the accuracy. Yeah. Are there any other questions? Yeah. What's that? Battery life currently, so we have 3 batteries to power the whole system. One is for the mobility base, the yellow robot that you see. Second is for the excavation, and third is for the compute. Right now, the compute is very, very heavy. So the compute lasts for about 2 hours on this battery system. And that's the limiting factor here. Otherwise, the excavation and mobility can last about 4 hours. Yeah. Yeah. Yeah.
What are the challenges with technologies on a spot and building a firm specific?
Yeah, so it's quite challenging, especially because the lunar surface can have a lot of craters. That's also partly where our senior crater grader team comes in, where they built a robot which can grade the work site pretty easily. And there's also this particular robot, the base we're using is the Husky base from the ClearPath Robotics, and it has a pretty good maneuverability here. So, but going forward for an actual flight system which will actually go to the moon, we'll definitely need to have much more research on the wheels. Yeah. 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 So the how quickly the drum fills while we collect the material is pretty dependent on how fast we rotate the drum. If we rotate it too fast, then the sand will start also falling out of the scoop that we have. And if we rotate it too slow, it will just take a lot of time. So there is an optimal velocity to rotate the drum. Currently, we are just eyeballing it, but for autonomy, we plan to do further tests for it. Yeah. Yeah.
So your perception stereo cameras, it looked like the drum was occluding when it came down.
Yeah.
So why did you place the cameras there?
So this camera that we have will be used both for mapping, for figuring out where to dump, and also to evaluate the berm that we're building. The thing is, this camera has a good view of the berm in a specific pose of the excavation drum. If we lift it up completely and then we place our robot in a particular manner, it can see the berm completely, even sometimes the back of the berm. Yeah.
To add on, if you make the camera a little lower, it will also obstruct, like the dust will settle on the camera and that will obstruct the view.
What was the momentary chattering saw on the
Yeah, so that's part of the autonomy thing that we have to work on, because if we take the drum too low into the sand, it will start, it affects the belt that is driving the drum. So the belt is not taut, like tight enough when it goes too deep. That's why it stops rotating.
So for the full semester,
Yeah.
is the plan to use mapping to assess kind of the scene in front?
Yeah.
And then that information then somehow is translated to what you're going to do with the drum?
Yeah. So we are also using the camera to estimate the height of the drum, where it is, and where it should dump, place the robot in a manner that we can dump accurately. So that's all part of the autonomy stuff.
And the camera is the only sensor you plan to use for that?
For this, yes, currently, yes. Also, if anybody after this presentation wants to excavate and drive a robot, feel free to. We have the joystick there, and you can have fun with the robot if you want. Yeah. Yeah.
Estimate the amount of dirt that you scoop, like the mass estimation.
So we don't have it currently, but we've done extensive testing on how we can estimate the amount of material that we have. We found that the current, the integral of the current over a specific period of time of both the actuator, which is lifting the drum, and the motor that is driving the drum, are a pretty good estimate of how much sand there is inside. Yeah.
We have a question from Zoom. So it is, what are the challenges we see when it comes to localization when compared to Earth and in the moon? So the key challenge we face for localizing in a terrain such as the sand is the wheel slip. So the encoders alone will not be very reliable because the wheel slip is very significant. So we are using the total station to compensate for the wheel slip. And the total station alone will not be sufficient because it's not very continuous data. So we need both the encoders and the total station for accurate localization.
Are there any additional steps in order to create persistent regolith structure? Like Crater Grader team taught me that the sand isn't that different from the particles on the moon, and that's not eternal, right? I mean, a blast is going to smooth it out, things like that. I don't know. Are there ideas of it's needing to be treated in some way in order to make it more lasting?
This should not require any treatment. Like, although we've only tested it with the sand in the sandbox, but going forward, unless and until it's like a really sticky substance which won't fall out due to gravity from the drum, it should be fine. For the any coarse material like this, particulate matter should be fine.
This cannot be directly used.
Yeah.
Right.
So we are just using the angle of repose to build basic structures, basic berms.
Yeah.
Right.
This is only to
Build
evaluate.
stuff on top of it, it's gonna have some compliance, right? That's, I'm
Yeah.
not saying you should do it, I'm
Yeah.
just wondering what the overall concept is for building on this.
So building on the moon, a few plans that even NASA has currently is that they can use this regolith to fuse with certain chemicals to make 3D printing material, which they can have to build.
Then I guess the maximum height of the berm for your project
Yeah.
won't exceed whatever.
Yeah.
height
Yeah.
of-
Yeah.
Okay, you're not gonna be climbing on something to add more.
So the thing is, we wanted to, but there's not enough sand in the sandbox to try that. Otherwise, this robot should be capable of even building sand mounds and climbing on top of them to build bigger structures. We just don't have enough sand here to test.
Another place where this fits in is like even for processing the 3D printable material, we can use this to construct berms near the processing facility, so that the 3D printable material can be processed.
Not just for building, but also for collecting all the material to be later used for building. There aren't any other questions?
The fastest
Thank you.
demo ever. What's going on?
Yes.
Thank you.
Well, last time we got the feedback that we should build faster, so we built faster. Yeah. Yeah, if you want to drive the robot, that's completely fine. Yeah. Yeah. Thank you. Thank you so much for attending the demo.
It's like moving, right?